So thanks for the introduction. And in this talk, you will hopefully learn how to build memory-efficient 3D maps and how you can use these maps later on, for example, for navigation planning, collision avoidance, or tasks like localization. Is this loud enough with the microphone? Okay. Closer? Okay, I'll just do it like this. So with the recent availability of affordable 3D sensors, we tend to see more and more robots actually operating in the 3D world. So we're beginning to see less and less of these wheeled mobile platforms with the 2D laser rangefinder, but actual robots performing tasks like mobile manipulation, mapping of outdoor terrain, of underwater or caves, tasks like humanoid navigation, which I'm mostly interested in, but of course also obvious applications like disaster response. For these environments, since these are typically highly unstructured, what we actually want is some sort of 3D environment representation or a 3D map. What do you want this map for? Well, you've seen the movie talk before, so to actually perform tasks like mobile manipulation, we need collision-free navigation, we need localization, but also things like exploration, which is especially crucial for these disaster scenarios, are typical applications of these 3D maps. And if we think of a 3D environment representation, then what are typical requirements that we have in mind? First of all, what we want is a probabilistic representation, which we also know from 2D occupancy mapping. So we want to handle sensor noise, we want to handle dynamic changes in the environment, so we can react to these changes with our planning algorithm or our collision avoidance. And also, we may want to fuse multiple sensors in this map. Then, ideally, we want to represent both free and unknown areas in addition to the occupied measurements, so we cannot just take point clouds and regard them as obstacles, because this doesn't allow us to reason about the free space, which is between the sensor and the endpoint. And this is really crucial for collision-free navigation, where the robot should only navigate in the safe area that it has explored before. But it's also useful for exploration, so we can find the sort of boundary to the unknown space where the robot should go next, or where the robot should look to in order to explore that space. And last but not least, we want to handle efficiency in a 3D map, since this is no longer 2D, and the data grows more and more dense, and we want to have high resolution, of course, so we want to have a compact memory representation of this 3D data, so a robot can store this map in memory or on disk or for exchange between robots. And also we want efficient access to the data structure. So these are some requirements which we had in mind when we designed this OctoMap framework. The obvious choice as a data structure there is the octree. It's also in the name. What is an octree? An octree is a tree-based data structure. On the right, you see an example of this kind of octree. At the top is a volumetric representation, and at the bottom you see the same octree as a tree-based representation. So it's really the same representation of the same data structure. And we see already that this is really nice to encode volumetric data. You'll also see that you have a recursive subdivision of the space. We have this single measurement here, and it's this tree is recursively subdivided into 8 octants. So each voxel in the space can be refined incrementally by subdividing it to its 8 children. And these children don't have to exist. What you see here, the whole left half of this cube hasn't been observed by the robot, so there's no information encoded there, as opposed to these 2 big chunks which were observed as free. So this gives us the possibility, by implicitly encoding the unknown space, but with missing information, to differentiate the safe and free areas from the unknown areas. And what's also nice about this tree data structure is that it can be allocated as needed. So as the robot explores new areas, the tree grows into this direction. And we don't have to allocate all the memory at once, as we would have to do, for example, with a 3D voxel grid. Now, this is a binary representation of free and occupied. If we now think of using octrees for 3D occupancy map, we actually want to store some sort of occupancy probability in the nodes, so we have a probability that this portion of the space is occupied. If you do this in an octree, so now we're storing probabilities, then we actually can perform 3D occupancy mapping. We have a volumetric 3D model given by the octree. We will have probabilistic integration. It will be memory efficient, as we will see in some sample data sets. And you'll also have a flexible extension of the mapped area, which we won't have with a fixed size voxel grid. And also the nice thing is the octree here is encoding the same information as a 3D grid, but it's doing it much more efficient, because a 3D grid really has to be filled to contain all the space. So all this would have to be filled, whereas when we only have the endpoints in there, or the free space in between, we're having much less information stored in the octree. So some more details on OctoMap framework is it's based on octrees. We have a probabilistic representation of occupancy, including the free space, and the unknown space is implicitly represented in here. It supports multi-resolution map queries, which is a nice property if you want to do anytime collision checking or anytime planning. So as we will see, we will get a nice speed up by doing coarser queries on the octrees. And it offers a lossless compression and compact mat files. You see an example, octree created from one single laser scan of a robot standing in a hallway here. So what's important here is that we're not only encoding the occupied areas, which you see on the left, but also the free space in between the robot. It was standing here and doing a scan with a tilting laser. So we know which areas the robot has seen. For example, through the door here, it has observed portions of the next room. So when I'm showing you octree maps, keep in mind that we're not always showing the free space, but it's really encoded in the octree. What you also tend to notice on the right is that we'll have multi-resolution voxels here. We're not having the smallest ones only. You see on a corner. Here are some bigger ones. Here are some bigger ones. So all the free space, even from this single scan, we can exploit this lossless compression by pruning children of a node, which are all identical. So all the free space within this this octree is consisting of all of these big voxels, and only at the corner we're having the smaller voxels. And this is really the nice property, which will lead to the memory efficient compression. Some more properties of our framework. It's open source license, BSD, so quite permissive if you want to use it for commercial products. Implementation is C++ with a very low set of dependencies. So if you have CMake and C++, I would say that you can already compile this, and you can actually compile it for Linux, Mac, and Windows. It's fully documented. Code is on GitHub if you want to check it out or want to fork it and contribute new features. And thanks to the nice ROS build farm and the release system, Bloom, we're having pre-built Debian packages for ROS Electric up to the upcoming Hydro already available. So you don't actually have to compile this yourself. You can just install the Debian package. So OctoMap itself is a standalone library. It's been used in a couple of things in ROS. So to make this easier, we have ROS integration in OctoMap ROS, OctoMap Messages, and the OctoMap Server package. So you don't actually have to use ROS, but it's really written in a way that you can easily use it in ROS. And as we've seen in the last talk, what's really nice is that if you're using OctoMap, you can directly employ collision checks in FCL, the flexible collision library, and it's directly running in MoveIt. These are some advantages. So further details, we have a publication which has been recently accepted to the Autonomous Robots special issue on open source software for robotics. So if you want to look up some details which are not covered by the talk, check out the paper. It's also linked from the OctoMap homepage. So let's get to some details to give you some understanding on what's happening under the hood. So what we want to do, as I mentioned before, is we want to model occupancy in this map. And we do this by employing the binary base filter, which was introduced by Moravec in '85 for 2D grid mapping. And we're essentially applying this to 3D maps. What you see up there is the formula for the binary base filter. It's a static state-based filter, so it assumes that the environment doesn't really change. If we now switching to using log odds instead of probabilities, we can get rid of all of this, and our measurement update converts to a simple addition of the new values up to the old values. And this, for once, is more efficient to perform, and the other thing is that it's numerically more stable if you have small probabilities. Then to ensure updatability with this static state base filter, we're enforcing, or we offer you this clamping policy, which you see at the top, which means that probabilities will have to be in a certain range. So there's the minimum probability and the maximum probability. When a node's occupancy reaches the lower probability, it will stay there. It won't get less probable or more probable. And with this, we can avoid an overconfidence into a map. So if you consider you have a robot that measures this door as to be closed 20 times, then when the door suddenly opens, you don't want to measure this door at least 20 times open to integrate that back into your static state binary base filter. So by limiting the maximum and the minimum probability, or the log odds, we are ensuring that the map stays updatable. Then we're also updating the inner nodes, and we're doing this to enable multi-resolution queries. So each inner node will have the maximum occupancy of its children. This is a quite conservative setting, so we don't risk bumping into obstacles. And by doing this, and you're traversing the octree to generate visualization or a collision model, then you can just stop at the inner nodes to obtain a coarser representation of the octree. This is the same map data, and we're just stopping traversing the octree one level before the leaf. And if we do that less and less, we get a coarser representation, and we will get this faster, and this will also make your collision checks faster if you do this. And finally, we have the compression property, which you see illustrated at the bottom for a quad tree. So wherever there are nodes which are kind of identical, they will be merged into the parent node, and we can throw all the children away because all the information is losslessly encoded in the parent node. So this is how we update single cells of the octree, or single voxels. Now with the range sensor, we want to reason about the space between the robot sensor origin and the endpoint, so we can know what is free and what is occupied that we've seen in the world. And to do this, we employ raycasting here. This is potentially an expensive operation, since you have to update all the space between the origin and the endpoint. You have to compute these voxels, so not integrating a single measurement, but all the way. So this really depends on how long your measurement beams are. This is just to keep in mind. This is what makes the holistic update expensive in the end. So there's something to optimize in here. And we're marking the last voxel to be occupied, so we are increasing the probability, and we're marking all other voxels on the ray to be free, so we're decreasing the probabilities or the log odds. This is implemented in the compute ray function or in the insert ray function if you want to actually insert a single ray measurement into the octree. And now if you don't need all this reasoning about free space between the robot, then you can just update the endpoint and all your octree updates will be faster immediately. So this is one of the bottlenecks to keep in mind for map updates. So typically what we get from a sensor is not a single ray, but a complete 3D point cloud or a depth image. This is also the case if we have a laser, which is a kind of sweeping laser on a pan-tilt unit. And what happens there is on the left you see an example for a noise-free simulated 3D scan. And if we now integrate this 3D scan ray by ray into our octree, it will look like this. And this will be exactly the same if you use a 3D occupancy grid. So the problem here is that we're observing the floor or any kind of surface at a shallow angle. What we actually want to have is this. So every occupied endpoint should be integrated to be occupied into the map. What happens is with the sweeping laser, or if the order of updates of your 3D point clouds happen in the same way, is that you will measure this voxel to be occupied and everything else to be free in between. And when you do the next update of the same scan, suddenly your occupied voxel will get decreased in probability, and eventually, after a couple of measurements, it will disappear, even though this is the same scan it's inserted. So our solution for this is to update each voxel of one complete point cloud at most once, where we give a preference to occupied endpoints so that we can ensure that everything that's occupied in the scan will end up to be occupied in the map. And this is implemented in the insert scan functionality in Octory, which was also more efficient because it's a batch insertion than inserting single rays. Once you've built a map, now what can you do with it? We don't want to build map just for the sake of building maps. We're going to do something with it. Whatever you want to do with it, we have some methods of accessing this map data. And the most efficient one, just as inserting the scans batch, is traversing all the nodes with iterators. This really works similar to a C++ standard container, like a vector. So you'll create a leaf iterator in this case, and you'll iterate over the octree, and all the information that's required will then be reconstructed while you're iterating the octree. And with this, we don't need to store anything in the octree that we don't need beyond the standard probabilities. Notice that here you're accessing the iterator directly. So the iterator will give you the coordinate of the node where you're at right now, whereas the node only knows its value, which is in this case the probability stored in it. And there are other iterators which you can find out about in the documentation. For example, traverse all inner nodes. This is only traversing the leaf nodes, or traverse only nodes in a certain bounding box. And all these iterators can be accessed with the maximum depth, so you can perform this multi-resolution map queries. Finally, or as a second example for accessing data, we have ray intersection queries. This is essentially raycasting on a built map, which is useful for visibility queries, but also for localization, where you have a range sensor and you want to check out from this position how likely it is that you actually observe an obstacle over there. And you could do this with the cast ray function. And well, as a final example, of course, you can also search for single nodes just by looking up their coordinates, x, y, z. But this, if you have multiple queries, will be the least efficient one because it will traverse the tree every single time. So we'll end over traversing the tree multiple times from multiple queries. So if you can, use the iterators for it. One thing to notice here is you're getting back a pointer, but this pointer can be null, and this is the case if the node doesn't exist. You're asking the octree what is at position x, y, z, and if you get null back, then this is an unknown area which hasn't been observed before. So you can do this to differentiate between unknown areas and free areas. When the node exists, it's either occupied or free. And by getting back the values, you'll get back the probabilities. Or by asking the octree, which is the second example, if the node is occupied, you'll get back if it's an occupied node or free node based on the probability parameters of the octree, which you can set with an example on the top. And you can also check if the node is at the threshold, at the clamping threshold, the lower or the upper one. Some more implementation details. I'll only go over this briefly. The core class is octree. This is an occupancy octree. It's storing the probabilities. You'll notice that all of this is templated, so you can easily extend it to your own implementation. And actually, we're also already providing this color octree as an example how you can do this extension. Well, this octree is using floats to store the log odds, which denote the probabilities. In addition to this, you'll see the color octree is having some color attribute, which you can use for visualizations or for integrating kind of data color point clouds from the Kinect. So most of the common functionality is in the occupancy octree, so you can easily derive from it and build up your own octree data structure, whatever you have in mind. You'll also notice that the octree nodes only store the data that's actually only necessary, which is a value, a certain kind of data, that's the payload that's stored in the nodes, and a pointer to a child pointer array. This is everything you need to build up this octree. They're not storing their own coordinates. This would really blow up the memory. You also notice this strange construct of having a pointer to an array of pointers of children. The nice thing here is that we can have the same class for leaf nodes and for inner nodes, which will allow us multi-resolution queries. But at the same time, it will allow us to save memory because leaf nodes only have one unused null pointer, which you can use to find out that it's a leaf node, whereas inner nodes will have one extra pointer with 8 child pointers. And this allows us to actually save up to 60 to 80% of the used memory. So one other very popular use case is writing map files once you've recorded them or built them in your own mapping application. Then you can write out the full octree to an OT file, which is an octree file. But if you're only interested in the maximum likelihood, which is sufficient for collision checks, for example, then you only need to encode the difference between free and occupied. In this case, you can write the BT file, which we call the bonsai tree. It's really tiny in the end. It will be a couple of kilobytes large only. You see, again, our example octree here at the top. This is what part of the octree looks in memory. And this is what the complete binary stream for the BT file will look like. So we're using only 2 bytes. We require 2 bytes for each level of the octree. So only 2 bits for each node to differentiate between a free node, an unknown node. You see it here. This is free. This is unknown. There's nothing there. And an inner node, which will be recursively reconstructed while reading the binary stream. This just, how we get these small file sizes, and you can just call this with octree write binary, and it will do this serialization to the binary stream, which you can also use for message exchange between different nodes in ROS. Then the reverse case, reading map files. Since we have this general structure that an octree can actually count anything in there, you can do your own extension. We have this factory pattern here, which you see at the top example. In an OT file, you can store any kind of octree. So you need to use this abstract octree to read from a file. It will give you back a pointer to an abstract octree. And then you need to check if the read was successful, and then dynamic cast to the kind of class you're expecting. And this is the case since you don't really know what you're reading from the file until you look at the file, right? But if you have a BT file, then there's usually an octree in there because it can only encode probability or occupancy information at the clamped values. So this is a bit easier to read and write, but you're not able to store any kind of probabilities or color information or anything else in the BT file except free and occupied. So since we're all interested in ROS here, we have a couple of convenience and helper functions to make this easier in the case of using ROS. We have the OctoMap messages packages. There's an OctoMap message in there that you can use to send around octrees between different nodes in your ROS system. And to serialize and deserialize, there's a conversions.h. Again, this looks very similar to the previous slides. To serialize, you're calling full map to message or binary map. This is the OT file, and this corresponds to the BT file. You're serializing this octree into this message, and then you can send it out. And this will really exploit all the properties we've seen before in the file. So this is the same as storing a file and sending it out. To deserialize, again, notice that this looks like the factory pattern we've seen before. So we're calling the message to map function in conversions.h, and then need to dynamic cast to the octree. This again this will look if it's a binary tree or not. So you can just call this on any kind of octree message. The message can contain a binary tree or a full octree. There's a flag in there to denote the difference, and then you'll get your octree class out of the serialized message. So map visualization is really important since this is 3D data and it's a bit harder to understand sometimes than just a simple 2D projection or in an image. We're bringing our own native visualization application based on OpenGL and Qt. But of course, since we're using ROS, maybe more interesting for you will be RVis. In OctoMap server is the class you can use to send out, or the ROS node you can use to send out files. Then it's also sending out a 3D visualization as a marker array that you can then display in RVis. However, just recently, Julius Kammerl of Willow Garage wrote a native RVis plugin. It's in the OctoMap RVis displays package. So you should really check this out. I think it's being released starting with Groovy. So with this, RVis can natively display OctoMaps, so you don't need to convert them to some intermediate format like marker arrays, which again will be pretty large and inefficient. So the RVis plugin will deserialize the tree, and create the visualization for you. Or even better, if you're using MoveIt, this is directly integrated in the MoveIt planning scene visualization. So it will display the OctoMap for you. So one example use case, or some sort of tutorial how to do 3D mapping in ROS with OctoMap. There's the OctoMap server for you. If you're not using MoveIt or haven't yet switched to MoveIt, it will integrate 3D point clouds by building incrementally an OctoMap representation. It will send out this representation on service requests or as messages, and will also send out a visualization. What you need to do there is listening to the cloud in topic, which needs to be a point cloud too. So you need to remap the topic to your actual data coming from the sensor. And what's also important is that you need a TF transform from the map frame to your robot sensor frame. So your robot needs to have some sort of localization or other pose estimate. And there's an example on file that you can look into. And here's an example that we've worked on here. The now is mapping this environment with an ASUS action sensor, which is mounted on the top. So it's walking around, mapping the environment, and integrating the data in OctoMap to building a collision map, which contains all the obstacles that you see over here. So I really want to stress this, since I get a couple of requests, like I've seen OctoMap, I want to do 3D mapping, how do I do this? I have a robot, I have a sensor, how do I do this? So this is not an integrated mapping system. I think we're not at a point where we can just plug and play any kind of 3D SLAM system to build up magically 3D maps by just putting a sensor on the robot. So OctoMap here is doing one part, and this is the mapping. It's mapping with known poses, so it needs a pose estimate. It's converting or integrating your point clouds into 3D occupancy maps. It's not an integrated 3D SLAM system that you can just start and it will do everything for you. So it needs the TF from the sensor to the map frame. Some examples that you can use is, for example, a 2D localization with G-mapping or AMCL in ROS. That's been running great on the PR2. If you have a good odometry, then this is sufficient as well. You can use a package like RGPD SLAM, which does the SLAM for you and publishes the poses, or any kind of other SLAM system. So there's really room for more research or more development there. So since OctoMap is a standard CMake project, you'll include this and use it just as a standard CMake library. So in your CMake lists, you just need to find OctoMap, include directories, and link libraries, and that's it. For us, you also need to add this to your manifest if you want to release, or for the new Catkin build system to your package XML. And additional packages to use are OctoMap messages and OctoMap ROS. So finally, to conclude this part of the tutorial, look at the API documentation. It's available from the OctoMap homepage for further details on how you can use all the classes and all the functionality in there. And if you're not using the latest version, you can also always compile your own documentation by running make docs. So let's look at some properties of the library, or how we can do mapping and how it will perform on various datasets. We'll have all these datasets and evaluation instructions online. So if you want to work on some improvements or want to compare your mapping algorithm to it, then you can look at our datasets there and compare it. The source here are usually 3D laser scans, since this was the robot and the sensor we had at the time we built the datasets, in and outdoors, small scale and large scale. So here's an office building. This is building 79 at Freiburg campus. You've probably seen this in a couple of 2D SLAM datasets already. Here, the Octane memory is only 42 megabytes. This is the complete map at 5 centimeter resolution, including the free space, which you don't see visualized here. If you compare this to a 3D grid, it's at 80 megabytes, which is still okay, but this is very, very well aligned, so a 3D grid will be play nice here. Here we have a large outdoor data set. This is the complete computer science campus at Freiburg. This is the building 79 you just seen before, so it's quite large, up to 300 meters into the longest axis. And this in memory is only 130 megabytes, including free and occupied space. If you compare this to a 3D grid, if it's optimally aligned and you're doing this one-shot grid integration, it will be 650 megabytes in memory. And you also see that the BT files are really, really tiny. All this, I think that the PNG file is even larger than the OCT-tree, which is encoding all the 3D information. There's one more. This is from the new college data set, epoxy. It's a similar data set with a different sensor setup. So here we don't have pan tilt laser, but instead it's using a sweeping laser to the left and right of the robot. So it's mapping the environment as the robot advances. Similar properties, this is only 50 megabytes. There's less of free space encoded here, so it's a bit smaller. You see that the robot didn't see anything here, so it's not encoded in the map, whereas the 3D grid really needs to encode all of this and in the tiny bounding box. So here's a final example. This is an indoor environment. This is an office which was built, the data was built with a Kinect and then aligned with RGB SLAM. Here we're encoding the color information, so it's a bit larger. So each node is not only encoding the probability, but also RGB values. So this whole office, 8 by 7 meters, 5 meters in height, of the mapped area at least, is 46 megabytes. The OCT-tree is 22 megabytes writing to file, including the color information, or if you drop the color and you write a BT file, it's only half megabyte large. The memory usage for several resolutions, you see that here for the Freiburg campus. Yeah, it's the Freiburg campus. This is a log axis, so we're still having a exponential dependency on the memory. We can't really change that, but we can change the order of magnitude. What you see here over here is the 3D grid at 10 centimeter resolution. It will be 5 gigabytes in memory. So this is already larger than any 32-bit system can actually store in memory. Whereas the OCT-tree is 1 gigabyte large if you use OCT-tree compression, and if you use only the maximum likelihood OCT-tree and keep it in memory, you can perform a more efficient compression, which will go down to 500 megabytes at the smallest resolution of 0.1 meters, 10 centimeters. So if you change the resolution, of course, you'll need less memory. Now, in terms of efficiency of updating the map, of course, we have to perform ray casting. So we need to spend some time calculating the rays and updating all the voxels in between. Here we see the map update time averaged over 100,000 points. And what you also see is that this really depends on how long your beams are. In the Freiburg campus, we're using a SIG laser rangefinder, having range measurements outdoors up to 50 or 80 meters. So this contributes a lot to this update time, where it takes a second to integrate 100,000 points. Now, if you truncate this, and you're updating only up to a certain range, I think this is 10 meters, which is still sufficient for outdoor mapping if you're integrating a couple of scans, then it becomes a lot faster. Or what you can also do is you can change the resolution. What you also should keep in mind is if you have a Kinect or very dense point clouds, then it makes sense to subsample them before you integrate them in OctoMap. Otherwise, it will do raycasting for every endpoint and integrate this. Then to access the map data, you'll see that on the right. This is using the iterators, so it's running through all the OCT-tree in 50 milliseconds. Not doing anything, just running through the OCT-tree. What you also see here nicely is that the depth cutoff really pays off. We're saving about half the time by using a coarser resolution. So 0 cutoff is we're using the full OCT-tree, going down to the leaves at the smallest resolution. If we don't need this, if you have a map which is 10 centimeters, but you're fine with using 20 centimeters for your collision check, then this suddenly will be twice as fast. So finally, I'm coming to some applications, example use cases of OctoMap. What I've worked on is the 6C localization of a humanoid robot using an OctoMap of the environment, which was built beforehand. See the environment here. This is an AR robot with a laser rangefinder, and here we implemented some Monte Carlo localization based on laser, IMU, and joint angle data. And this is also available in ROS. If you're interested in this use case, you should look at this package. It's also released open source, and the sensor model here is raycasting in OctoMap, and this is directly running in OctoMap. So if you just want the sensor model, look into OctoMap, the raycasting functionality. So here the now is in its home environment, a scaled down unit environment. Now we're doing global localization in the OctoMap. You see particles all over the place, and after integrating some measurements, this converges to the true pose, which you see at the top left in the corresponding video. So it's integrating a couple of scans, and it becomes more and more accurate. And despite this really noisy motion of the now, we have quite some drift there on this hardwood floor. We can accurately estimate the 6D pose while it's walking. Okay, I'll skip over that for the sake of time. The next use case, I'll not go into detail much here, is tabletop manipulation or even mobile manipulation. We've seen it in MoveIt. There used to be a collider package which was doing this for ARM navigation. Now it's directly running in MoveIt and running in like up to real time, updating sensor data. You'll hopefully see this at the booth with the PR2. You can really jump in and it will stop motion planning and replan around you. And here OctoMap is used as a probabilistic collision map, updating from stereo or laser data or just the Kinect. And this enables dynamic updates of the collision map while the robot is running. And the nice thing here is you can directly collision check on OctoMaps with FCL or MoveIt. Another use case is navigation in clutter or mobile manipulation. Here we're building also a collision map with OctoMap, updating it while the robot drives around. If we then perform whole body collision checks of the complete robot mesh model, this enables us to actually drive the robot autonomously to a table, to dock under it. It doesn't need to be teleoperated. And it also will allow us to traverse narrow passages. I'll just show the video. Here, this is the 3D obstacle map. You see there's lots of clutter. This is kind of lab environment at Willow Garage where people are sitting and working and putting up their chairs and all kinds of stuff. So this was built beforehand. So the robot can plan in this, but it's updating while it drives around. And you'll see now that it drives to the table to pick up the basket. This is a predefined motion, the pickup motion, but everything else is planned and executed autonomously. And this was a joint work with Sachin at Willow and Gil and people from Maxim Likachev's lab, where here we're using the search-based planning library to perform these holonomic motions. This is the path that the robot computed using these 3D collision checks. Now, since 3D collision checks are expensive, we implemented a speed up where it's using multiple layers of projected 2D maps from the OctoMap to rule out collision checks. You're still preserving the flexibility of performing whole body 3D collision checks, but you can speed them up by maintaining several layers of 2D projections which represent the robot. So, for example, you have one layer corresponding to the base, which is really kind of this compact shape. And if there's a collision there, you don't need to perform any 3D collision checks. And here you see this challenging part where it has to move sideways. Since it couldn't really put the basket away, it needs to slide under the table with the base. Will be exciting to see. I think this could be implemented in MoveIt nowadays in, I don't know, Johan, what do you say? A couple of days. One day? Okay. Some extensions. I'll only show you these briefly. There are octree hierarchies presented by my colleague Kai at IROS 2011. Here we have local submaps we have multiple OctoMaps with different resolutions, and this allows us to move them independently with different coordinate origins. And all my other colleagues, Christoph and Boris from Freiburg, they worked on 3D distance maps, which you see here based on OctoMap. They can be incrementally updated, so this could be a nice use case for collision checking. You'll see the distance map displayed here. And this is also already available in the OctoMap distribution. It's not yet released into ROS, but you can get this dynamic EDT 3D from the OctoMap homepage bundled with OctoMap. So I'll get to the summary of these past 40 minutes. I present a memory-efficient map data structure. If you haven't seen it before, this is OctoMap. It's a volumetric representation of occupied, free, and unknown space. The implementation of common map functionality is already in there, so you can do sensor updates of your range data or single rays. You can do ray casting for localization. It's all open source, BSD license, and has a tight integration into MoveIt and ROS and FCL for collision checking. And whatever, just leave me a message if you have some nice use case for it. We're always happy to see like how you can use OctoMap. Things we think of as localization and collision avoidance, but maybe there's another nice use case. Thanks for your attention.